In this video, I will show you the detailed operation of ECL or NOR circuit. This is the circuit structure of our ECL or NOR circuit. Here you will see from the same circuit I can take the NOR output and the OR output. Therefore, this is our ECL or NOR circuit. In this circuit, you will see the transistor QA, QB and Q2 will form a differential amplifier, and the operation of this logic circuit will be depending upon the operation of our differential amplifier. Here you see the emitter terminal of transistor Q2, QB and QA are coupled or connected together. Therefore, this will be known as emitter coupled logic. And with minus 5.2 volts supplied at this terminal, a fixed amount of current will flow through our resistor RE, which is 1 kilo ohm, and that current will be denoted as IE, and the value of IE will be more or less constant, and it will be around 3 milliampere. Therefore, in some ECL circuit, you will see this RE is replaced by an independent current source. The fixed current IE is allowed to flow through the collector terminal of the transistor QA, QB and Q2 depending upon the logical input at this terminal or this terminal. Therefore, this IE equal to 3 milliampere will switch its position from the collector terminal of transistor QA to collector terminal transistor QB or the collector terminal transistor Q2, as this IE equal to 3 milliampere current is allowed to pass through any of the collector terminal depending upon the logic levels. Therefore, the circuit will use the current switching principle. Therefore, the ECL circuit is sometimes abbreviated as current mode logic or CML circuit. Now, let's say the current that is flowing through this transistor QB is IB. The collector current of the transistor QA equal to IA, and the collector current of the transistor Q2 is I2. Therefore, if I apply Kirchhoff's current law at this terminal, you will see summation of incoming currents IA plus IB plus I2 will be equal to our IE. The transistor QA, QB and Q2 will form our differential amplifier, and the transistor Q3 and Q4 will form our emitter follower circuit. See, the output terminal of the coupled collector terminal of the transistor QA and QB is connected to the base terminal of the transistor Q3, and the collector terminal of the transistor Q3 is connected to ground, and the collector terminal of the transistor Q2 is connected with the base terminal of the transistor Q4, and collector terminal is directly grounded. Therefore, the transistor Q3 and Q4 will act as an emitter follower circuit. For logic 0, in case of this ECL circuit, I will apply minus 1.7 volt, and for logic 1 I will apply minus 0.8 volt. Now let me describe the logical operation of this ECL OR and NOR circuit. At first I will talk about logic 0. A will be at logic 0 and B will be at logic 0. A will be at logic 0, that means I will apply minus 1.7 volt between the input terminals to the ground terminal. Okay, now see, as our input will be at logic 0 and this will be at logic 0, therefore our transistor QA and QB will be in off state or in cutoff mode. So when the transistor QA and QB will be in cutoff mode, their collector and emitter terminals will act like open switch. Therefore, I can disconnect the collector and emitter terminals from the given network. As a result, you will see the collector current of the transistor QA, which is IA, will be equal to 0, and the collector current of the transistor QB will be equal to 0. Here it seems that the IA, IB and I2 are the emitter currents, but in case of a bipolar junction transistor, emitter current is approximately equal to the collector current. So I can use the collector current and emitter current, the word synonymously. As the current through this path and this path will be equal to 0, you will see this I1 should be the sum of the collector currents. I1 should be the sum of collector current IA plus IB. Therefore, it will be equal to 0. That means there will be no current flow through the resistor R1. As the I1 is equal to 0, you'll see from this terminal to this terminal, our voltage I1 R1, this will be equal to 0. So there is no voltage drop from this terminal to this terminal. Here I am applying minus 5.2 volt between this terminal to this ground terminal. That means I am supplying a voltage source whose value is 5.2 volt, whose positive terminal is connected here and the negative terminal is connected here. See, from this terminal to this terminal, as the voltage is equal to 0, therefore the 5.2 volt will be appeared between this terminal to this terminal. Here you will see this 5.2 volt will be absorbed by the base to emitter junction of the transistor Q3 and the 1.5 kilo ohm resistor, as the base terminal of the transistor Q3 will have a voltage of 5.2 volt. Therefore I can expect that the transistor Q3 will be in active region, because in a ECL circuit our transistor will never saturate. Therefore I can expect a base to emitter junction drop greater than 0.7 volt, which will be, let's say, 0.8 volt between this terminal to this terminal, and the rest of the 4.4 volt will be absorbed by the 1.5 kilo ohm resistor. See, from this terminal to this terminal I will get minus 4.4, and from this terminal to this terminal I will get 0.8 volt, and from this terminal to this terminal I will get 0 volt, so minus 5.2 volt. Okay, now see, if I denote this voltage with VO2, here you will see VO2 will be equal to, from this terminal to this terminal it will be minus 0.8 volt, and from this terminal to this terminal the voltage is 0, minus 0, which will be equal to minus 0.8, which indicates that for input of logic 0 0 I will get logic 1, which is the NOR output. In a NOR gate, if I apply 0 0 I will get output as logic 1. As our transistor QA and Q2 are in off state, our transistor Q2 will be in active region. When the transistor Q2 will be in active region, I will get the collector current through the collector terminal of the transistor Q2, and here I will use the collector current I2 and the emitter current of the transistor Q2 synonymously, because in a bipolar junction transistor collector current IC should be nearly equal to our emitter current IE. Therefore you will see this IE will flow through the collector terminal of the transistor Q2, and this same IE will flow through the resistor R2. As I2 will be entering from this direction, so this terminal will be positive and this terminal will be negative, as I2. Here the IE, which is equal to 3 milliampere, will flow through the collector terminal of the transistor Q2. Therefore our emitter current IE should be equal to our collector current I2, which is equal to 3 milliampere. Therefore I will get a voltage drop I2 R2. I2 is 3 milliampere and R2 is 300 ohm. So here I will get 0.9 volt between this terminal to this terminal, 0.9 volt. Okay, between this terminal to this terminal. As I am getting 0.9 volt between this terminal to this terminal, but here we are applying 5.2 volt between this terminal to this terminal. Therefore the rest of the 4.3 volt voltage will be the voltage between this terminal to this ground terminal. So I can say that the base terminal of the transistor Q4 will be at a voltage of 4.3 volt, which is sufficient to drive the transistor Q4 in the active region. So when the transistor Q4 will be in active region, its collector and emitter terminal, its base to emitter junction drop will be 0.8 volt, and the rest of the 3.5 volt will be absorbed by the 1.5 kilo ohm resistor with this terminal positive and this terminal negative. So from this terminal to this terminal I will get 3.5 volt, and from this terminal to this terminal I will get minus 0.8 volt, and from this terminal to this terminal I will get minus 0.9. so if I add them up I will get minus 5.2 volt. Now what will be the voltage VO1? See, the voltage between this terminal to this terminal I will denote that with VO1. From this terminal to this terminal I will get minus 0.8 volt. From this terminal to this terminal I will get minus 0.9 volt. Therefore I will get minus 1.7 volt, which indicates logic 0. So this will be our OR output. Now let me talk about this case when our A will be at logic 1 and B will be at logic 1. That means I will apply minus 0.8 volt between this terminal to this terminal and minus 0.8 volt between this terminal to this terminal. As I am applying logic 1 at the input terminals, therefore our transistor QA and QB will be in active region, and our transistor Q2 will be in off state or in cutoff mode. As the transistor Q2 will be in off state, its collector and emitter terminals will act like open switch, so I can disconnect the collector and emitter terminals. Therefore the collector current I2 in case of the transistor Q2 will be equal to 0. As the collector current I2 will be equal to 0, therefore you will see there will be no current flow from this terminal to this terminal. Therefore our I2 R2 drop which is equal to I2 equal to 0 into 300, so it will be 0 volt. That means from this terminal to this terminal there will be no voltage drop, or voltage difference between this terminal to this terminal will be equal to 0 volt. Okay, now see, as VEE is equal to minus 5.2 volt, that means I am applying the positive terminal here and negative terminal here. Therefore you will see I will apply 5.2 volt at this terminal. Now as from this terminal to this terminal the voltage is 0, that means this terminal will have a voltage of 5.2 volt. As this terminal will be at 5.2 volt, this 5.2 volt will be appeared across the base to emitter junction of the transistor Q4 and the resistor of 1.5 kilo ohms. As the base terminal of the transistor Q4 is in 5.2 volt, therefore I can expect that it will be in active region. When a transistor is in active region, it will have base to emitter junction voltage greater than 0.7 volt. Let's say I expect that as 0.8 volt, and the rest of the 4.4 volt will be absorbed by this 1.5 kilo ohm resistor. Okay, so from this terminal to this terminal minus 4.4 volt, and from this terminal to this terminal minus 0.8 volt, and from this terminal to this terminal 0 volt. So I will get minus 5.2 volt between this terminal to this ground terminal. Now I denote this voltage with VO1. Now what will be the VO1? VO1 is the voltage difference between this terminal to this terminal. From this terminal to here I will get minus 0.8, and from this terminal to this terminal I will get 0. Therefore our VO1 will be at logic 1 for the input of 1 1. This is the OR output. Now consider this, as I2 will be equal to 0, that means IE equal to 3 milliampere current will flow through the resistor R1. Our I1 will be equal to 3 milliampere, and when it will be at this point, as our transistor QA and QB are active region, therefore it will divide. One will go in this direction and another will go in this direction. This current will be IA and this current will be IB. Here I am considering the emitter current and collector currents are equal, because in a bipolar junction transistor its emitter current should be very close to collector current, so I can consider the collector and emitter currents equal here. Okay, so here you will see this 3 milliampere current will divide here, and when this IA and IB will get into this point, they will be added up to equal to 3 milliampere. So I can write that our I equal to 3 milliampere will flow through the resistor R1 through this resistor, and the collector terminals of the transistor QA and QB, and the resistor RE. So here you will see our I1, which is the sum of IA IB, will be equal to IE, because here as the transistor Q2 will be in off state, this I2 will be equal to 0. So IE will be equal to IA plus IB, which will be equal to 3 milliampere. So this IA equal to 3 milliampere. Now what will be the voltage drop between this terminal to this terminal? See, I1 will be entering from this direction, so this terminal should be positive and this terminal should be negative. Our I1 R1 drop will be equal to 3 milliampere into 300, which will be equal to 0.9 volt. So from this terminal to this terminal I will get a voltage of 0.9 volt, with this side negative and this side positive. Now see, we are applying 5.2 volt between this terminal to this terminal. I am getting only 0.9 volt between these two terminals. Now the rest of the 4.3 volt will be appeared across this terminal to this terminal. Here you will see our base terminal of the transistor Q3 will be in 4.3 volt. As the base terminal of the transistor Q3 will be in 4.3 volt, I can expect that our transistor Q3 is in active region. Therefore I will get a voltage of 0.8 volt, which is greater than 0.7 volt between the base to emitter junction, and the rest of the 3.5 volt will be absorbed by the 1.5 kilo ohm resistor. Okay, see, from this terminal to this terminal I will get minus 3.5, from this terminal to this terminal I will get minus 0.8, and from this terminal to this terminal I am getting minus 0.9, which can be added up to minus 5.2 volt. Now the voltage at this terminal is VO2. What will be the value of VO2? VO2 is the voltage between this terminal to this ground terminal, okay, or this terminal. From this terminal to this terminal I will get minus 0.8, and from this terminal to this terminal, see, I will encounter negative terminal first, positive terminal later, so it will be minus 0.9 volt, which can be added up to minus 1.7 volt, which indicates logic 0, which is the NOR output. Okay, now consider this case when our A will be at logic 0 and B will be at logic 1. A is at logic 0 and B is at logic 1. That means I will apply minus 1.7 volt between this input A terminal to this ground terminal, and I will apply minus 0.8 between the input terminal B to this ground terminal. As I am applying 0 volt here, therefore our transistor QA will be in off state. As I am applying the input, as I am applying logic 1 at the input terminal B, therefore our transistor QB will be in active region. As we have the transistor Q2 is in active region, therefore our transistor Q2 will be in off state or in cutoff mode. Therefore I can disconnect the collector emitter terminals of the transistor Q2 and the collector emitter terminals of the transistor QA, because when a transistor is in off state, its collector and emitter terminals act like an open switch. Okay, therefore you will see the collector current IA will be equal to 0 and the collector current IB will be equal to, and the collector current I2 will be equal to 0. That means from this terminal to this terminal there will be no current flow. I2 will be equal to 0. As a result, you will see our voltage drop I2 R2 will be equal to 0. From this terminal to this terminal I will get no voltage drop. Therefore you will see, as we have VEE equal to minus 5.2 volt, that means I will connect a negative terminal and a positive terminal here and maintain a voltage difference between this terminal to this terminal equal to 5.2 volt with a voltage source. Therefore you will see, as I am applying 5.2 volt between this terminal to this terminal. As between this terminal to this terminal voltage will be 0, therefore 5.2 volt will be appeared between this terminal to this terminal. Therefore I can say that the base terminal of the transistor Q4 will be in a voltage of 5.2 volt. In case of ECL circuit, this transistor will be in active mode, therefore I will get a base to emitter junction voltage of 0.8 volt here, and the rest of the 4.4 volt will be absorbed by this 1.5 kilo ohm resistor. Okay, therefore see here, from this terminal to this terminal I will get 4.4, from this terminal to this terminal I will get 0.8, from this terminal to this terminal I will get 0. If I add them up I will get 5.2, or if I go in this direction I will get minus 5.2. Okay, now see, I will calculate VO1. VO1 is the voltage between this terminal to this terminal, therefore you will see I will get minus 0.80, minus 0.8 volt, which indicates logic 1. See, for the input of 01 our output is at logic 1. This output is our OR output. As in the circuit our I2 is equal to 0 and our IA will be equal to 0. IA is the collector current of the transistor QA and I2 is the collector current of the transistor Q2. Here I will use collector and emitter current synonymously, because in a bipolar junction transistor emitter current is nearly equal to collector current, so this collector and emitter current will be nearly same. Okay, so this emitter current IB will be our collector current IB here. Now see, as our collector current IA and IB will be equal to 0, therefore this IE will be equal to IB. This IB will be equal to 3 milliampere. If I apply KCL here, you will see our I1 will be equal to sum of IA and IB, which will be equal to 3 milliampere. Here this IA will be 0, but this IB will be equal to 3 milliampere. So I can say that 3 milliampere current will flow from this terminal to this terminal. Therefore I will get a voltage drop whose positive terminal will be here and negative terminal will be here. I1 R1 voltage drop, I1 R1. I1 is equal to 3 milliampere and R1 is 300 ohm, so I will get a voltage of around 0.9 volt from this terminal to this terminal. 0.9 volt with negative terminal here and positive terminal here. Okay, see, I am applying 5.2 volt between this terminal to this terminal. I get only 0.9 volt between this terminal to this terminal, and the rest of the 4.3 volt will be appeared across this terminal to this terminal. Therefore I can say that the base terminal of the transistor Q3 will have a voltage of 4.3 volt. As the base terminal of the transistor Q3 will have a voltage of 4.3 volt, I can expect that in case of this ECL circuit our transistor will be in active region. Therefore I can expect a voltage drop greater than 0.7, which I will assume as 0.8 volt between the base to emitter junction, and the rest of the 3.5 volt will be absorbed by this 1.5 kilo ohm resistor. So from this terminal to this terminal minus 3.5, from this terminal to this terminal minus 0.8, and from this terminal to this terminal minus 0.9 will be added up to minus 5.2 volt. So our voltage VO2, it is the voltage between this terminal to this ground terminal. VO2 will be equal to voltage between this terminal to this terminal minus 0.8 volt. Voltage between this terminal to this terminal, see, this terminal will be negative and this terminal will be positive, minus 0.9 volt. So here I will get minus 1.7 volt. For the input of 01 our NOR output will be at logic 0. Similarly we can consider the case of input A at logic 1 and B is at logic 0. In that case the transistor QA will be in on state and the transistor QB and the transistor Q2 will be in off state, and we can consider the similar case. There you will see our output will be here at logic 1 and here it will be at logic 0. Okay, that's it. Thank you.